Welcome to this explainer. Today, we're diving straight into Form 3, Chapter 6, Geometry, and we're unpacking the absolute magic of angles and tangents of circles. Now, if complex geometry diagrams have ever made you feel, well, a little lost, trust me, you're in the exact right place. We're going to build a visual toolkit together, step by step, making every single rule and formula completely logical, and honestly, super easy to remember. So let's get into it. Okay, here's our game plan for today. We'll start with angles inside the circle, then move to exploring cyclic quadrilaterals. After that, we hit the power of tangents, followed by solving complex circle problems, and wrap it all up with a final chapter revision summary. Starting off with Section 1, angles inside the circle. Starting from the center to the circumference. All right, so when we're dealing with circles, the absolute foundational rule is all about angles subtended by the same arc. If angles share the exact same base arc on the edge, they are completely equal, no exceptions. But check out what happens when we compare an angle hitting the outer edge to one hitting the dead center. If you take that same arc and draw lines straight to the center of the circle, that central angle, it's always exactly twice the size of the angle at the circumference. Literally a perfect 2-to-1 ratio, every single time. It's kind of wild how consistent that is. And it gets better, because the size of an angle is directly proportional to its arc length. Just look at the ratio we've set up here. If a 2-centimeter arc creates a 25-degree angle, expanding that arc to, say, 6 centimeters means we simply scale up. Since 6 is 3 times larger than 2, we just multiply 3 by 25. And boom, we find that our new angle x is exactly 75 degrees. The arc is literally driving the size of the angle. Now, let's talk about a very special, almost magical number in circle geometry, 90. If you draw a straight line all the way across the circle, the diameter, splitting it into 2 perfect semicircles, and then use that diameter as your base arc to draw an angle to the circumference, well, that angle will always, without fail, be exactly 90 degrees. It forms a perfect right triangle right there inside the circle. This semicircle rule is an incredible shortcut for quickly solving unknown values when you're stuck on a test. Moving right along to Section 2, exploring cyclic quadrilaterals, shapes drawn on the boundary. First things first, let's define what on earth we're actually dealing with here. A cyclic quadrilateral is a 4-sided shape, sure, but it has one very strict condition. All 4 of its corners, or vertices, absolutely must lie exactly on the circumference of the circle. When they're all perfectly touching that outer edge, this beautiful kind of mathematical harmony just locks into place. And what is that harmony? Well, it's perfectly represented by the number 180. In any cyclic quadrilateral, the interior angles directly opposite each other, like straight across the inside of the shape from one another, they will always add up to exactly 180 degrees. It's a super reliable rule. It lets us easily solve for missing pieces of the puzzle just by knowing what's going on in the opposite corner. But wait, there's actually an even faster shortcut. If you take one of the lines of that cyclic quadrilateral and just extend it right outside the circle, you create an exterior angle. The rule here is incredibly elegant. That exterior angle, it is exactly equal to its corresponding opposite interior angle. Yep, you instantly have your answer without having to calculate a single thing. It is a total game changer for speeding up your problem solving. Next up, Section 3, the power of tangents, stepping outside the circle. Okay, so we need to be really precise about what a tangent actually is. A tangent to a circle is a perfectly straight line that just barely skims the outside of the circle, touching it at one, and literally only one, single point. Recognizing these straight lines in a chaotic exam diagram is honestly the very first step to unlocking the rest of the geometry puzzle. Once you spot one of those tangents, your next move is to immediately look for the radius. Why? Because when the line drawn from the center of the circle, the radius, meets a tangent at that one single point of contact, it forms a perfect 90-degree right angle, every single time. This right angle is basically your master key. It unlocks the rest of the diagram and helps you figure out the remaining angles of any attached triangles. Now, what happens when you have 2 tangents that originate from the exact same point out in space and they both touch the same circle? You get beautiful, perfect symmetry. Notice how the lengths of those 2 tangent lines, from the starting point all the way to the circle, are exactly equal. And it doesn't stop there either. The angles formed by drawing lines to the center are perfectly mirrored too. Because of these right angles and symmetrical sides, we can actually pull in trigonometry to easily solve for unknown radii. Pretty cool, right? All right, brace yourself for a rule that tricks a lot of students. It's called the alternate segment theorem. When a chord, which is just a straight line crossing the inside of the circle, meets a tangent, the angle they form on the outside is exactly equal to the angle hidden away in the alternate segment inside the circle. Visually, it's like a direct copy-paste from the outside to the opposite inside segment. Once you know exactly where to look, it lets you skip the complex math completely. Moving to Section 4, Solving Complex Circle Problems, bringing the toolkit together. So let's see how this all actually looks in the real world. Can we trace the logic using the rules we just uncovered? Let's take a look at a mechanical pulley problem right now. I highly encourage you to pause and really test your new skills here. Okay, here is how we break down a complex, messy diagram into logical steps. Step 1, identify your circles. We've got two pulleys here centered at points O and A. Step 2, note the straight lines. We have a ceiling, BC, which is acting as our tangent, and a connecting rope, ADO. Step 3, apply the toolkit. Ask yourself, where do the radii meet the rope and the ceiling? Boom, at exactly 90 degrees. By carefully tracing these right angles and tangent properties step by step through the whole diagram, we can easily calculate that missing value of x. It's just a giant puzzle. Finally, Section 5, Final Chapter Revision Summary, your KSMM Geometry Toolkit. All right, let's do a rapid-fire review of these golden rules so you're ready for exams. Angles subtending from the same arc, always equal. The central angle, exactly twice the size of the circumference angle. Angles hidden inside a semicircle, a perfect 90 degrees. For cyclic quadrilaterals, those opposite inside angles always sum to 180 degrees. When you step outside, remember a radius always meets a tangent at exactly 90 degrees. And finally, the alternate segment rule, where that outside angle perfectly mirrors the inside one. You now have the complete visual map of Form 3, Chapter 6. But I want to leave you with a thought. As you walk around today, look at bicycle wheels, architecture, or even machinery. Where else in the real world are these hidden geometric circles and tangents lurking, silently holding our entire built world together? Keep your eyes open and keep discovering.